Today I'm going to talk about cyclicity preserving operators on spaces of analytic functions. I hope that everybody is able to see the mouse cursor in the slide. So yeah, let's start talking about what cyclicity is. I'm going to be focusing on cyclicity with respect to the shift operator for the purpose of this talk. So the basic framework of this talk surrounds on the space X of analytic functions on an open set in Cn. And for the introduction part, I'll just say that the space X is reasonable enough, but I'm going to justify what I mean by reasonable enough later. So I have a space X of analytic functions on this open set in Cn. And I say that a function f in X is said to be cyclic if the shift invariant subspace generated by f, which is defined to be the closed linear span of monomial multiples of f, where z to the alpha represents the monomial z1 to the alpha 1, z2 to the alpha 2, and so on up to zn to the alpha n. And I just write alpha as the n-tuple of non-negative integers, which is represented by z plus n over here. So the shift invariant subspace generated by f is the closed linear span of these functions. And by linearity, you can check that this is same as the closed linear span of polynomial multiples of f. And I say that function is cyclic if all of these equal to the whole space X, meaning that polynomial multiples of f are dense in X. That is how people generally view shift cyclic functions. Obviously, shift cyclic because it kind of depends on the shift operator, as you can see over here that this function can be achieved by applying shift operator one after the other and obtain the monomial multiple of f. And cyclic functions have been studied for a long time. They have been tied to a lot of deep problems in mathematics. My personal interest came through Nikolsky's paper, which was about the relation between cyclic functions in the Hardy space for any number of variables to something called the periodic dilation completeness problem, which is a problem about completeness of a certain set of vectors in your usual LP spaces on the real line. I won't get into too much detail over there. I'll just mention a few facts about the Hardy spaces before we go in, because I'm going to use them as the basic example of some of the general results I'm going to talk about. And for convenience, I'm going to denote the set of all cyclic functions in X by Cx or C, depending on the context. So let's start talking about Hardy spaces. As usual, I'll denote the unit polydisk by Dn, which is the set of all vectors in Cn such that each coordinate has absolute value less than 1. And Tn represents the n-torus, which is also called the distinguished boundary of the unit polydisk, which is just a set of all vectors in Cn such that absolute value of each coordinate is equal to 1. I'll also denote sigma n by the normalized Lebesgue measure on Tn. And with this, we have the following definition. For p between 0 and infinity, we define the Hardy spaces as the space of all analytic functions on the unit polydisk that satisfy an LP growth condition radially. It's very similar to the LP spaces. In fact, all of these HP spaces become closed subspaces of LP on the n-torus. We also have the space H infinity, of course, that we know and love, which is a space of all analytic functions on the unit polydisk that are bounded. We know that for p between 1 and infinity, HP is a Banach space with the following norm as in the definition. So for the case when n is equal to 1, meaning in the case when you have Hardy spaces on the unit disk, cyclic functions were characterized using Berling's theorem, which further depends on the canonical factorization theorem for Hardy spaces, which says that every function in the Hardy space on the unit disk can be written as a product of something called an inner function and outer function. And what happens when p is between 0 and infinity is that the set of our cyclic function coincides with the set of our outer functions. Okay, and both of these functions, inner and outer, are sort of reasonably well understood. And this is what brings a sort of an algebraic structure to the Hardy spaces in one variable. But for n greater than 1, we know that this is not true. In fact, neither of these theorems hold true. Particularly interesting is the following example by Rudin, which says that the following two variable function, e to the z1 plus z2 plus 2 over z1 plus z2 minus 2, is outer in H2 of the bidisk, but is not cyclic, which shows that the Berling's theorem criterion does not hold true. Note that both inner and outer functions do make sense for n greater than 1. So it does make sense to ask if you have such a canonical factorization or even Berling's theorem. What is true is that the cyclic functions are outer in Hardy spaces. So one direction is true, but the other direction is not known to be true. And the thing that I find interesting about this example from Rudin is it uses a bunch of operators from one Hardy space to the other, mostly composition operators, and he shows that some of these operators preserve outerness, some of these don't. And there's a small trick involved in there which shows that this function is outer but not cyclic. So it kind of was interesting to me to try to think of operators that preserve these type of structures like cyclicity and outerness and all that. So along those lines, I was able to find a few results on operators that preserve cyclicity, meaning TF is cyclic whenever F is cyclic. But they were obtained using a lot of different contexts. Like it wasn't exactly what I was interested in. So the first result that I could find was by Gibson and Lamoury, who showed that all operators T from H2 to H2 that preserve outer functions, and hence cyclicity, because in the one variable case, we know that outer and cyclic is the same. All these operators have to be weighted composition operators. And then soon after, Marcheggi and Ransford generalized this to the entire range of HP spaces where P goes from 0 to infinity. And both of these results sort of used an algebraic approach. It used something called the Gleason-Cahin-Zarasko theorem. For those of you who know about it might be interested in checking that out. But it still used the specific properties of the Hardy spaces in the one variable case, like the Berling's theorem and canonical factorization theorem, that could not be used in Hardy spaces in more than one variable or even general spaces. However, for other spaces of analytic functions, Marcheggi and Ransford proved a different theorem, which sort of shows that this phenomenon of outer preserving functions is actually a specific case of a more general theorem about weighted composition operators, which says the following. So suppose I have a space X, which consists of analytic functions on the unit disk and satisfies properties x1 to x3, which are as follows. So x1 says X contains the set of polynomials as a dense subspace. X2 says that for every point in the unit disk, the point evaluation is bounded or continuous. And X3 says that X is shift invariant, meaning multiplication by Z is closed in X. So if your space X satisfies these three properties, and you have a subset of X which satisfies the following two properties, that if G is an element of X which is bounded above and below, then G belongs to Y. And all these affine maps where lambda is inside of the unit circle also belong to y. So you have a specific set of functions in x. So okay, go back to theorem statement. Suppose x satisfies x1 to x3 and y is a subset of x that satisfies these two properties. If we take T, a continuous linear map from X into the holomorphic functions on the unit disk, such that the image of every function in Y is non-vanishing. That is what this means. Like T of G is non-vanishing for every G in Y. Then there exist functions phi and psi such that T of F is the weighted composition operator psi times F of phi. And note that this psi is a non-vanishing function itself because it is the image of the constant function 1. And this was interesting to me because this sort of sheds an interesting light on what happens to certain set of functions under weighted composition operators. And it might be an interesting way to look at weighted composition operators themselves. However, I was able to notice that these properties x1 to x3 have more to provide in terms of obtaining this result instead of having to look at a specific subset of y. So in sort of desperate attempt to get something for the Hardy spaces in more than one variable, I was trying to work around a way of avoiding all the algebraic stuff that was used in some of these results and trying to provide a more natural way of looking at what's exactly happening between weighted composition operators and functions in this space. So that was kind of the motivation, and the main point of this talk is going to be trying to generalize this theorem for more spaces of analytic functions and also over other domains, not just the unit disk or the polydisk. So for the basic notation, I'm going to fix an n natural number, and I'll take an open set inside of Cn. I'll take a Banach space, subspace of holomorphic functions on D, which satisfies the following properties. These are going to be very similar to x1 through x3, as you saw in the previous theorem. P1 says the set of polynomials is dense in X. The bounded linear functionals are dense, are continuous. Sorry, bounded. The point evaluations are bounded, sorry. And the third condition is that all of these shift operators corresponding to each variable zi is a bounded linear operator, so that we can talk about cyclicity. Now, note that property P1 implies 1 is a cyclic function in X, right? Because the shift invariant subspace generated by 1 is going to be the closure of the polynomials, right? The shift invariant subspace was a closed span of polynomial multiples of the function, and polynomial multiples of 1 are just the polynomials themselves. So it's pretty obvious that 1 is a cyclic function. And if f is a cyclic function, then 1 belongs to the shift invariant subspace of f, obviously. And that implies that f is non-vanishing, because if f was not non-vanishing, say it vanished at a point z, then every function in the shift invariant subspace would vanish at that point z, which would contradict the fact that 1 is in that space, because 1 is non-vanishing. So we have some trivial necessary conditions over here for cyclicity. Simply f is non-vanishing, which will be useful later. Examples of spaces include the Hardy space, as we discussed before. We also have the Dirichlet type spaces, which is given by set of all functions that are analytic on the unit polydisk that satisfy this nice weighted norm, weighted little L2 condition on the Fourier coefficients. Dirichlet type spaces consist of examples like the usual Hardy space H2, the Dirichlet space, and also the Bergman space, etc. And just to give an example of a space of functions over a different domain, we also have the Drury-Arvidsson space, and also the Besov-Sobolev spaces work as well. on the unit ball of Cn, they satisfy properties P1 through P3 as well. And there are many more. Okay. So the main preliminary result we get for the spaces is about the action of a certain type of linear functionals. What do I mean by that? So let's say I take my space X that satisfies P1 to P3 over the open set D that I chose. And I pick a bounded linear functional lambda such that its action on these exponentials e to the wz is non-zero for each w. Note that w and z are both vectors in Cn, and this dot represents the dot product, but I'll just use wz for the sake of simplicity. So w dot z is going to be like w1 z1 plus w2 z2, and that multilinear sort of term. So if I have a function like this, then there exists a point A, which is non-zero, and a point B in the right heart spectrum of the shift operator, which I'll define in a moment, such that lambda restricted to the set of polynomials is sort of a weighted kind of point evaluation. So it's a constant multiple of a point evaluation at that point B. Note that we cannot guarantee that B belongs to D directly, and I'll talk a little bit about that after the proof of the theorem. For those of you who are unaware, the right heart spectrum of S is the complement in Cn of the resolvent of S, which is this set, which is a set of all vectors in Cn such that you have an n tuple of operators on X that satisfy this condition. Okay. Just this algebraic condition. And it's a bit technical where I'm going to use that in the proof. I'm not going to dig too deep, but I'll just provide all the arguments for the sake of completion. First thing to note from the statement of the theorem is that it's not immediate that these functions belong to X, because I've only assumed P1, which says that polynomials are in the space X and that they are dense. So we kind of have to justify and be careful when we say that lambda of these exponentials is non-zero. But it's easy to see, as we can see from this lemma, that for each w, this function belongs to X. And in fact, its truncated power series converges to the function in X. So pk is the truncated power series, meaning I stop at the total when the total degree is less than or equal to k, and I call it pk. And the proof of this is simple. First, we show that pk just converges in X because this series converges absolutely, as you can see. So if I take the absolute, the sum of the norm of each of these individual terms of the power series, I can bound this whole thing with the norm of, the mod w to the alpha, which is just mod w1 to the alpha 1, mod w2 to the alpha 2, and so on, times norm s to the alpha, which comes from taking the norm of z to the alpha, times the norm of 1. And that can be represented as this quantity, which is finite. So the series converges absolutely, and hence converges because X is a Banach space. But if it converges to G pointwise, if it converges to G in X, then by P2, pk converges to G pointwise. And the pointwise limit of the truncation of the power series is e to the wz. So combining those two, we can show that it converges to e to the wz. So with that in mind, we now prove theorem 2. Recall that we had these linear functions that satisfy this property, and we want to show that restricted to the polynomials, they are similar to point evaluations. So since lambda is continuous, and we saw in the lemma before, I can take lambda inside the summation when I write the power series for e to the zw, and I can obtain this relation. Now I'll take lambda sub alpha to be the image of z to the alpha under lambda, And note that the absolute value of lambda alpha can be controlled with this expression. Okay, so absolute value of lambda alpha is less than equal to the norm of lambda times the norm of z to the alpha. And the norm of z to the alpha can be controlled by this, because you can apply the shift operators repeatedly to obtain z alpha, and I take the norm each time. Okay, why am I doing this? Well, now what I'm going to do is I'm going to convert this thing into an analytic function of w. So I'm going to look at this expression as a function of w instead. What do I get? So if I define f of w to be this function, by the relation on the coefficients, I can conclude that f is a non-vanishing entire function such that this particular growth condition is satisfied. And I can just do that by taking the summation, by taking the sum of the absolute values of these terms and using this condition on the coefficients. So it's fairly easy to obtain. And from there, we can say that this implies that exists an A naught in C and a vector B in Cn, such that f of w is given by e to the A naught plus b dot w. Now there's a small question mark over here. It's not entirely obvious. We know something like this holds true for n equals 1, but trust me when I say that that result follows, this result follows from the one variable case. You just have to consider one variable slices. Instead of w, you can put like lambda w, and then look at this whole thing as a function of lambda and use the one variable result, and it works out nicely. So I'm going to skip the details because it's technical and not very fun, to be honest. So yeah, and this only works when you have non-vanishing entire function. In the one variable case, it works without the non-vanishing stuff, but it doesn't work when n is greater than 1. Non-vanishing entire functions in more than one variables are kind of easier to deal with. Okay, so then using this definition of f of w and this thing that we got, we can compare the power series coefficients, and we obtain that lambda alpha can be given by this nice expression. So it's a constant multiple of b to the alpha. Writing it down separately, we can easily see that for every polynomial p, lambda p is then going to be given by this expression by just taking linear combinations of this equation. Okay, so note that the only thing we now have to see is that the point B lies inside the right heart spectrum. And the way I'm going to show is I'm going to suppose that B is not in the right heart spectrum, and I get this n tuple of operators for which this is true. And I'm going to provide a contradiction, and the contradiction I'm going to show is that lambda of 1 is 0, which cannot happen because lambda of 1, the constant function 1, is a, and a was chosen to be non-zero. So that's what I have in mind. And in order to do that, I'm going to take this condition I got from the n tuple of operators, and I'm going to evaluate both sides at the constant function 1, and I get this condition, not condition, but equation regarding 1 being equal to a linear combination of certain functions that have this particular factor in them. So since I know that my linear functional evaluates to something nice on polynomials, I'm going to approximate these functions a1 of ai of 1 with polynomials, and I'm going to pick my approximation sort of cleverly in order to get a nice answer, as we all like to do. So don't worry about this term over here. I'm just approximating the functions ai of 1 by polynomials in order to get this approximation for 1 in terms of linear linear combination of polynomials with this factor in them. And the approximation is kind of nice. Now what I'm going to do is I'm going to apply my functional lambda on this and obtain the contradiction. How so? Well, first note that this approximation for the function 1 I got evaluates to 0 under lambda just by the representation, because when I plug in b for this polynomial, all of these zi's are going to turn to bi's and I get 0. essentially. So then we get the absolute value of lambda1 is the same as lambda1 minus lambda of this polynomial. If I take the appropriate bound, since lambda is a bounded linear functional, I get this whole thing is less than epsilon. And since epsilon was chosen to be arbitrary, that means A equals lambda1 is 0, which is a constant, which is a contradiction. And so the point B belongs to the right heart spectrum. So nothing too crazy happening over there, but it would be great if we can show that this point lies in the domain, because all we know, the condition we have on our space X is dependent on point evaluations on the domain. So we don't know what the functions behave like around the spectrum, although we at least know that it's contained in a nice sort of surrounding of our domain. Consider the Dirichlet space when alpha is greater than 1. One can see that the point B can be chosen to be in the closed unit polydisk, because bounded linear, the point evaluations are bounded even on the boundary of the unit polydisk in that case. So a natural question that at least I felt like need to be answered was, can functions in the space X be defined on all such points B in a reasonable way? So is it possible for me to somehow make sense of the function, of any function, not just polynomials on the point B that I just obtained? And the answer is yes, and it depends on something called the maximal domains. So I'm going to define what maximal domains are, but I should point out, I got this idea from a paper I was reading by, I think it was by John McCarthy, Michael Hartz, and a couple others. Sorry, I don't remember the names of everybody. Apologize for that. And they talk about different notions of maximal domains, depending on what kind of structure you want from your space to be extended. For the purpose of this talk, I'm going to restrict to this definition, which, I mean, I couldn't find it anywhere, but so I kind of came up with this weird definition, and I'll explain what it means. So I have my space X that satisfies P1 to P3 over the set D, and we define the maximal domain of functions in X to be the following set D hat, which consists of all W in Cn such that the point evaluation at W on polynomials has a bounded linear extension to all of X, meaning it consists of all the points B from the previous theorem that I want to study. I mean, this doesn't help anything. This is just rephrasing it. But now at least I have an idea of what domain I want my functions to be extended to. So first things first, it's obvious that D is a subset of D hat because all point evaluations on D are bounded. So naturally D has to be a subset of D hat. And by the previous theorem, I just showed that D hat has to be a subset of the right heart spectrum. I mean, it's not exactly obvious, but it's the same argument as proving B is a point in the right heart spectrum. So that means that this maximal domain I have is sort of contained around my domain, and it's not too big. Now, this isn't an obvious fact at all. For the Hardy spaces, one can show that D hat is equal to the whole space. It's equal to the unit polydisk. And it depends on the existence of certain type of cyclic polynomials on the boundary. I'm not going to go into too much detail because it's, again, not very interesting. It's just, something, it's kind of like bookkeeping almost. So for the Hardy spaces, you can show that the maximal domain defined in this way is the same as the domain you started with. Same is true for the Dirichlet space when alpha is less than or equal to 1. But as I said before, when alpha is greater than 1, things are kind of different. But even there, you get this nice space, the nice domain where you can extend your functions to. And in this case, it's kind of obvious, like the functions extend up to the boundary continuously anyway. So you might as well take D hat as your domain instead. Okay, so now I'm going to prove sort of an identification of my space X with another space X hat, let's say, which will satisfy properties P1 through P3 remember that my goal is to extend all the functions in the space X to functions that to a space which satisfies reasonably nice properties, because I still want to be able to talk about cyclicity and uh, uh, everything else surrounding it. So naturally, for every f in X, I'm going to define f hat, which is a function on d hat now, as follows. So what I'm doing is I'm taking the point evaluation at z hat on the polynomials and extending it to all of X. So over here, it's going to be lambda z hat p is defined as p of z hat, but then I can extend it to all of X, and by the abuse of notation, I can write lambda z hat f to be that extension. And it's natural to think of this as the value of the function f at z hat. So obviously p hat is equal to p just by the way we had defined d hat, right? For every polynomial, the evaluation is the same. And that f hat restricted to d is again going to be f, because lambda sub z for every z in d is just going to be, point evaluation at z, which makes sense for f anyway. You don't have to extend it and worry about the extension. Then I'll define x hat to be the following space of functions f hat, and I can endow it with the natural vector space. Just scalar multiplication and taking linear sums is fine under this operation. And naively, I can also define a norm on f hat to be just the same as norm of f. So convergent sequences in both the spaces are same. And then I can prove that this map that identifies X with X hat is an isometric isomorphism of Banach spaces. Okay. And we only need to show that the space X hat now satisfies the nice reasonable properties we want. And then from then on, we'll move to this sort of better space, better in quotes. So I'm not going to prove this theorem just because it's a lot of back and forth between the space X and X hat and just, writing out all the details, but I'll just write the theorem. So if I have a space X that satisfied P1 to P3 over D, then X hat above satisfies properties Q1 to Q3, which I'll define in a moment, over D hat, and is isometrically isomorphic to X with this map. Furthermore, X hat has the same set of cyclic functions as X. So the set of cyclic functions is preserved, and that's why we can move on to that space and forget about X, because we have the nice, nice statement about theorem 2. So the properties Q1 to Q3 are, first is the set of polynomials is dense, just as before. The second property is where things get a little bit different, but it's not too bad. So all the point evaluations are still bounded for every point in D hat. And if for some z in Cn, I have this point evaluation map on polynomials extends to a bounded linear functional, then z lies inside of D hat. Essentially comes out of the construction of D hat. And it's kind of cheating, but it's also preserving some of the properties from the previous case we had. So it can be regarded as an improvement overall. At least we now have an idea of how the functions behaved around that point, around the points in D hat. So we can still talk about cyclicity at that, not cyclicity, but how should I phrase it? Like how the function behaves around that point in the sense of going to the boundary and not blowing up or something like that. And the third condition is the same as P3, just that the shift operators are bounded for every I. Now, with this theorem in mind, we can rephrase or modify theorem 2 as follows. If X satisfies Q1 to Q3 over a set D hat, then all linear functionals that take these exponentials to a non-zero number have to be a constant multiple of point evaluations. And we can just bypass the whole right hard spectrum stuff. But at least we know now that the set D hat is like very contained. So note that since the Hardy space satisfies P1 to P3 and the maximal domain is itself, it most certainly satisfies Q1 to Q3 over D hat. And that's why theorem 4 holds for the Hardy space. Okay. So this was the basic setup of, you might think that I haven't yet talked about cyclicity or anything, but this is kind of like the basic setup you need. And this is similar to the methods for the one variable case as well. It's slight modifications in each step result into a sort of different looking answer. So using that theorem, I can prove the following generalization of theorem 1, which was Maastrichtian and Ransford theorem about the weighted composition operators. So now I have a space X of functions defined on the set D hat that are analytic in an open set inside of D hat and satisfies Q1 to Q3. I'm taking Y as a topological vector space of functions on a set E. Note that I'm not assuming that the set E or the functions in it are analytic or anything. They could be any, like it could be a random set, an abstract set as well, such that the point evaluations on Y are bounded at every point in E. Continuous, actually, I should say continuous because it's a topological vector space and not a Banach space. So it's a very general sort of space. Now, if I take an operator T, which is continuous between X and Y, then the following are equivalent. First thing is T of these exponentials is non-vanishing for each W. So all of these exponentials are being mapped to something non-vanishing. And that's equivalent to the second thing, which is T of F is the weighted composition operator given by some function A, which is non-vanishing, and F of B, where B is just an arbitrary, not really an arbitrary, but like some function from E to D hat. So if you remember the statement of Maastrichtian and Ransford's theorem, they had a sort of a subset Y, right? And the operator T was supposed to send all of the elements of that subset Y to something non-vanishing. Instead, I have something more tangible to work with. In this case, I have shown that you can just work with the exponentials instead of having to look at all different possible elements of Y. So just these functions work just fine. Okay, so that's the theorem. It's worth pointing out that A is the image of 1. Obviously, if I plug in F equals 1, this factor just gets removed and I get A of U. So A is the image of 1 and B can be realized as the n tuple of functions T of Z1 over T1, T of Z2 over T1, and so on. So that n tuple of functions. So both A and B can be found out just from the way it's defined. We all know that. Now for the proof, 2 implies 1 is straightforward. You just have to check. You just have to plug in E to the WZ for F, and you'll notice that this factor is non-vanishing because it's an exponential, and A is already non-vanishing. So 2 implies 1 is kind of obvious. And for 1 implies 2, you might be able to see what we are going to do. So I'm going to fix a point U in the domain of this space, and I'm going to extend this operator via the point evaluation on that point E. So now I'm going to take point evaluation on the set Y at U, and I'll compose it with that functional, and I'll obtain this functional lambda. And know that for each W, then lambda of E to the WZ is given by this composition, which just means evaluating T of E to the WZ at U. And since we assumed 1, we know that this function is non-vanishing, and hence you get something non-vanishing over here. So something non-zero over here. So then by the previous theorem, for each f, we can get, for each f, the following relation holds true for some a, u, and c, which is non-zero, and some point b, u, which is inside of the maximal domain. And since the choice of u was arbitrary, we get the desired functions a and b, and that T of f is this weighted composition operators. So the main part of the theorem was proving the general fact about the linear functions, and everything else kind of follows. Okay, so that's great, I guess. It should be noted that we have a complete, we have a proper equivalence between these two conditions. So now we are going to talk about cyclicity, preserving operators. Finally, the only thing we have to check is that these functions e to the wz are cyclic for every w. But again, it's quite simple. We want to find polynomials such that pk times e to the wz converges to 1. But if you choose pk to be the truncations of power series of e to the negative wz, you can use the triangle inequality and norm manipulations to show that e to the wz is cyclic, just with the choice of these polynomials. So I'm going to leave the details as well because they are simple. So we know that the functions e to the wz are cyclic, and hence this theorem follows easily from there, from the previous theorem. It says if x is a space of functions which satisfies q1 to q3 on d hat, and y is a space of analytic function that satisfies p1 to p3 now. So I want y to have cyclic functions as well. So I need some basic setup for y in this case. And I'm taking open set in Cm, m and n could be different as well. There's no stopping us. And if I take an operator T that takes cyclic functions in X and maps them to cyclic functions in Y, then we get the following relation, right? And it follows easily because instead of looking at all cyclic functions, I just look at e to the wz. And by the previous theorem, it would just give me this result. Note that cyclic functions in Y are non-vanishing. So I can use the fact that all exponentials of the type e to the wz are mapped to something non-vanishing and obtain this. And now in this case, a of t1 is cyclic, not just non-vanishing, right? Because 1 is cyclic. So the image of 1 is cyclic as well. And the function b has the usual representation. So this is kind of nice, but one thing to note is that the converse is not at all obvious in this case. It's not easy to determine when a weighted composition operator is going to preserve cyclicity. However, I was trying for the longest time to prove an equivalence, because we have an equivalence in the one variable case. And I was trying for the longest time to prove the equivalence for Hardy space, and I couldn't. Then I tried to switch to the Drury-Arison space because some people regard it as the correct generalization of the Hardy space in one variable. And a lot of nice properties hold true for cyclic functions in the Drury-Arison space, but even there I was not able to do it. But then I was reading an article that my advisor was kind of working on at the time, and I realized that I can actually prove that the converse is true for Hardy spaces, that all weighted composition or bounded weighted composition operators on every Hardy space is going to preserve cyclicity as well. And not only that, I'm going to prove something much more general. So the next lemmas are going to be a setup for that. So I'm just going to mention these lemmas and not going to the proof into a lot of the proof because I'm running a little bit short on time. So if I have a function in the Hardy space on the unit polydisk, and p is between 1 and infinity, then phi f belongs to the shift invariant subspace generated by f for each f in H infinity. So all H infinity multiples of f also lie inside the shift invariant subspace, which is just given by the closure of polynomial multiples of f. And that is kind of neat, and it uses like a Han-Banach separation argument. Then you regard HP as a subspace of LP, and you can extend this function gamma to all of LP. And by duality of LP, you can get at least one function H. I'm not worrying about the exact place where H lives, but I can get one function H such that for every G in HP or even LP, I get this relation where H belongs to LP prime, P prime is the conjugate exponent. And then I'll write phi as the weak star limit of some analytic polynomials pk. You can take fair means, for example. I'm skipping through the argument because it's not very important except for the statement. Then we can get a contradiction by showing that gamma of phi f is given by this. And since phi h bar is an L1 function, I can write this whole thing as the limit of the integral of pk f h bar. And by the representation of gamma on the shift invariant subspace of f, this integral pkf belongs to this shift invariant subspace of f, and hence all of these terms are zero themselves. And we get a contradiction. So this is a standard Han-Banach separation argument. And from there, we can get this following lemma, which shows that if I have a sequence fk of h infinity functions such that fk times f converges to g, which is a cyclic function in HP, then the function f has to be cyclic as well. And it's kind of simple now because fkf belongs to the shift invariant subspace by the previous lemma. SF is a closed subspace of HP, so it's the limit of fkf also has to belong to the invariant subspace. And since G is cyclic, F is cyclic, right? Because the shift invariant subspace of G will be a subspace of S of F. So it's kind of obvious that from there, F is going to be cyclic. And with that in mind, we get the following theorem, which kind of neat, I think. So suppose X satisfies properties Q1 to Q3 over D hat. And if I take an operator T that takes X into HQ of DM for some Hardy space, boundedly, right? And then the following are equivalent. T preserves cyclicity. If and only if TF is a weighted composition operator with this A being a cyclic function. So 1 implies 2 is a direct consequence of theorem 6. For the converse, assume that I take an f in Cx. I want to show that Tf, which is this function here, is cyclic. I pick polynomials that provide the cyclicity for f, meaning I take polynomials pk such that pkf converge to 1. Since my operator T is bounded, that implies T of pkf converges to T of 1. So T of pkf is given by this thing, just from, TF is given by A times f of B. So A times f over here is pkf, so pk of B times f of B. I'm going to separate this polynomial part out, and I get A times f of B, which is my TF. This is the stuff that I want to show is cyclic. And note that pk of B is an H infinity function now for each k, because the image of B lies inside D hat, right? Which is contained inside the right heart spectrum, which is a compact set. So pk of B is a bounded analytic function. So by the previous lemma, fkf converges to something cyclic. So this function has to be cyclic. Simple as that. So that proves this theorem. Like if you take an operator that preserves cyclicity from X inside of any Hardy space, when your Q is between 1 and infinity, then you can only do it using weighted composition operators. And this to me is interesting because the only way I have seen people try to construct cyclic functions is using some of these type of operators. Like you take a space and you map, you take a space in which you have a vague understanding of cyclic functions, and you try to understand the cyclic functions in the other space using these operators. So for me, it felt like very interesting to know that this is the best you can do. Like you can only work with weighted composition operators. How much time do I have? Oh, okay, I'm almost done anyway. So I just have a few conclusive remarks before I'll start taking the questions. It is possible to extend these results to non-Banach spaces. Uh, if you go back and look at the proof of the main theorem about the linear functionals, you can sort of see that I'm using the norm condition at exactly two places. One is when I'm finding that non-vanishing entire function and constructing it out of coefficients. Uh, if you remember that, that's where I use the norm. And the second thing is when I'm showing that d hat is inside the right heart spectrum. So for spaces like HP, when p is between 0 and 1, you still have a metric, and that seems to do the job just fine. You just have to go through and write down all the details a little bit carefully, and you can extend these results to HP spaces for p between 0 and 1 as well. Second thing I wanted to point out was, what about outer preserving functions? So note that the result that I proved about the exponentials and weighted composition can apply to a lot of different functions, different operators that preserve different sort of functions. Like I can take outer preserving operators instead of cyclicity, and ask whether all weighted composition operators preserve outer functions or not. And it's not true. Not all weighted composition operators preserve outer functions. So it would be interesting to know what weighted composition operators preserve outer function. And the last thing is, what are the general conditions on Y for the converse of theorem 6 to hold true? So remember that I was using a lot of facts about Hardy space, duality of LP, and all that. So I'm not sure what conditions on Y need to be in order for the converse to hold true. Here are some references if you want to check out. These are very interesting papers. I'm also citing a lot of things from Rudin's book if you want to check out Hardy spaces. And that's it for me. Thank you. Thank you for your attention.